Okay, let's take a look now at a new topic, which is referred to as chemical kinetics. And the chemical kinetics has two parts to it. Uh, the idea of reaction rates and the idea of collision theory. Now, we're actually going to work with these two in a different direction. We're going to start with the collision theory and then take a look at the rate reactions happen at. Now, collision theory states that molecules must have a collision physically in order to react. They cannot react with each other over a distance like gravity or a magnet. But what happens is that there's actually very few collisions that are successful. That's the bad news. The good news is that there are so many collisions happening between molecules in any given second that it makes up for the lack of success that actually takes place. Now the question is, why are these collisions, generally speaking, not particularly successful? And the answer is that you have to have physical collision, and often, particularly in gases, there's very great space between molecules, making it hard for them essentially to find each other. And then once they do collect, the atoms in the molecules have to be oriented in such a way that the bonds holding the atoms together have to be successfully broken. There has to be enough force. Often you can have a collision, which is like a fender bender, and not too much damage or not too much force gets applied between the molecules. So the speed of the collision has to be very, very high. When you do have the correct orientation and they have enough force, then the two molecules form what is called an activated complex. And it's this activated complex that transitions it from the reactants into the products. And when that happens, it's referred to as an effective collision. Now, here's why the orientation is so important. Take a look. They look like almost billiard balls, which is a nice analogy for it. Notice the potassium and the chlorine iodide have to be oriented in such a way that you effectively can pop off the CH3 molecule, kick it off the other side. Whereas if you have it the other way around, the CH3 portion blocks the potassium from getting access to the iodine, and therefore you'd have no reaction. So this illustrates nicely the idea that molecules, when they collide, have to be properly oriented, and that's just by chance. Now, if you take a look at BRNO, in this given case, there are several possible orientations that would lead to a successful reaction. Notice section A, or items A and B, work. But once again, there is a orientation which is shown in C, which in fact you would get no reaction because you have no appropriate orientation going on. Obviously, if there are multiple orientations possible, then you would have more probability that it would happen, and you'd have more successful rates of that reaction. Now, here's a very nice illustration of this whole setup.
When molecules collide, they form an activated In this reaction between nitrogen dioxide and carbon monoxide, the activated complex is NO2CO. The activation energy, which is the minimum energy needed to initiate this reaction, is 132 kilojoules per mole. At this point in the reaction, the bond between carbon and oxygen continues to strengthen, and the bond between nitrogen and oxygen continues to weaken. A bond is now formed between carbon and oxygen. The bond between nitrogen and oxygen has broken. The products of this reaction are nitrogen monoxide and carbon dioxide. The products are more stable than the reactants. The products have a lower potential energy. In this type of reaction, heat will be released by the reaction to the surroundings. The heat released by the reaction is 226 kilojoules per mole. This is an exothermic reaction. This is an energy profile for nitrogen monoxide, NO, reacting with chlorine molecules, Cl2, to produce nitrosyl chloride, NoCl, and chlorine atoms. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction. As the two molecules approach each other, an attractive force begins to form between the nitrogen of nitrogen monoxide and one of the chlorines of the chlorine molecules. This attraction is indicated by the dashed line. The bond between the chlorines begins to weaken, and the bond length increases. When molecules collide, they form an activated complex, a temporary species formed by the reactant molecules as a result of the collision before they form the product. In this reaction between NO and Cl2, the activated complex is nitryl chloride, NoCl2. The activation energy, which is the minimum energy needed to initiate this reaction, is 85 kilojoules per mole. At this point in the reaction, the bond between nitrogen and chlorine continues to strengthen, and the bond between the two chlorines continues to weaken. A bond is now formed between nitrogen and chlorine. The bond between the two chlorines has broken. The products of this reaction are nitrosyl chloride, NoCl, and chlorine atoms. The products are less stable than the reactants. The products have a higher potential energy. In this type of reaction, heat will be absorbed from the surroundings by the reacting mixture. The heat absorbed, or delta H, is 83 kilojoules per mole. This is an endothermic reaction.
One last idea to take a look at is the notion of reversibility. If you take a look at the reaction shown, the reactants A plus B require a rather large amount of activation energy or input to push the reaction forward to make eventually the product CD. That's very difficult. Therefore, the reaction in the forward direction is difficult because of the high energy requirement. Now, if we take a look at the reverse reaction, because remember, once you make products, C and D, they're zipping around everywhere also. They will have collisions with A, B, where nothing happens, but they will have collisions with each other also. And that collision has the risk of going the other way back to the reactants A, B. And so what you will notice is that the amount of activation energy required in reverse is less than the energy required in the forward direction. Result, this reaction is not going to be very successful going forward. It's going to be hard to get the product made because the product so easily goes in reverse to produce the reactants again. So this is an idea we're going to elaborate on, but to make sure you recognize that there's a different energy requirement in activation going forward than there is in reverse. So collision theory says, don't put your face in front of a soccer ball. It may hurt. Now let's take a look at a second idea. And the second idea is the issue of reaction rates. What that simply means is how quickly do the amount of reactants disappear? How quickly do the amount of products appear? If you take a look at this diagram in front of you, this is a very close-up image of a match head igniting. Now, when a match head ignites, there's a combining of sulfur with oxygen to make carbon dioxide and water. That reaction is enormously fast. We go from reactant, sulfur and oxygen, to product, CO2 and water, in an instant. However, rusting nails, where iron combines with oxygen to produce iron oxide, that is ginormously slow. So all reactions do not progress at the same rate. And we're going to explore how that happens. So kinetics is how fast the reaction proceeds. How quickly do I produce product? And again, this is an issue of reaction rates and the issue of reaction mechanisms, the steps involved in a reaction happening. The reaction rate is measured as a change in the concentration of reactants or products over time. And so it's a study in the molarity per second. It's the change in the molarity in a second. A, which are the reactants, going to B, products. So the rate of A is the delta A, which is the change in molarity of A in a certain amount of time. Notice it's a negative. It's a negative because there's a loss in the reactants towards the product. And so the rate is a negative value. The rate B, which is how quickly the product forms in a certain amount of time. Notice it's a positive because the product is being gained. Now let's take a look graphically, and these are very important graphs. You're going to be asked to work with them a lot, so it's important you understand what they mean. Take a look at the graph it sets up. The x-axis is time, which can be measured in seconds, and the y-axis is the number of molecules. You could also write it down as the molarity. A, you will notice, is the reactant, and therefore A starts on the top part of the y-axis because we have reactant, and as you might suspect, the product, which is B, it's going to start off at 0 because we have no product until the reaction begins. Let's take a look at this graphically over time. In the upper left area, you will notice at time 0, the black, which is the reactants, is all reactants and there is no product. However, after a certain amount of time, B, which is in red, starts to appear. And so what happens is when A decreases, you have a graph that starts to drop. B, which is red, begins to increase because we're making product. Now, as the reaction progresses, we are going to be increasing B and A decreases. Eventually, the whole process moves forward. Now, what you might want to note right now, it's going to be an important idea, is the amount of reactant in the end never goes to 0, or almost never goes to 0. And the reason why is the reaction from A to B, it's possible for some of the product B to go back to A. We saw that in the previous slides where the collision between products B with B could be successful and give you A. The result is it is almost impossible to completely get rid of the reactants A, and of course it's almost impossible to get nothing but pure B, which is the product. What else you need to note is that these graphs are not straight lines. They rather are what are called asymptotic. Now the reason why the production of product, which is B, that's the red line, the reason why it tapers is because after a while some of the B goes back to A. Now, the more product you have, the easier it is for a product to become reactant, and so it slows down. So the rate of A dropping is negative, the rate of B is increasing. Now, here's what we got. Here we got N2 plus 3H2 produces 2NH3, so it's nitrogen gas and hydrogen gas producing ammonia. Now, what we're going to look at here is look at the coefficients that are in front of these, the ratios. So you can notice that over time, H2 gas is dropping. Notice that the N2 gas drops, but it doesn't drop as rapidly. Why is that? The answer is because there are 3 H2 gas molecules being consumed for every N2 gas. The result is we're going to burn through that N2 gas very quickly because we use so much of it comparatively to N2. So the line of H2 is below or faster than it is for the N2. Now the number matters. What you do is you take a look and say that the N2 is 1/3 as quick because the hydrogen is being burned 3 times faster. Now the production of the NH3 also tapers out, and it goes up 2/3 as fast as the hydrogen. So notice the coefficients tell you how quickly these lines are going to be dropping or increasing. So the reaction rate is the rate at which the reactant disappears, or it's the rate at which the product appears. And notice that the rate that they change is proportional to the stoichiometry. So what you see here is that the O2 gas is going to be 1/2 as fast as the NO2. Now, if you want to get aggressive with this, you will obviously be able to take a tangent line. And the tangent line is going to be giving you the slope at any given point that the reaction is happening at. We will not be taking derivatives of these lines, but to point out that we are talking about a rate function here. Here, look at the data on the left. It shows you at time 0 what the concentration of the Br2 is. That's the initial concentration. Notice that as time progresses, the concentration of the Br2 gets less and less. And you can actually calculate what that rate is by taking the final minus the initial rates of the two. So to calculate the average rate, we take the Br2 concentration the end minus the Br2 concentration initial, divided by the T final and T initial. So Mr. Kurth, are you saying we're going to be given this data chart and be expected to calculate the average rate of change? Why, yes, you are. But it's a straightforward idea. It's showing you the concentrations of the Br at different times, and you punch in your numbers. Obviously, from a calculus standpoint, you can calculate from the derivative the instantaneous rate. We will simply use the data from the data table. So, what is the reaction rate using stoichiometry of A becoming B? So we have 2 moles of A disappearing for every B mole that is formed. So the rate is equal to 1/2 change of A over change in delta T. And the rate is 1/1, which isn't shown because that's 1, change in B delta T. So if you were to lay this whole thing out, the rate of change of reactant A is 1 over A delta T. That will be the same as, you could simply use the 1 over B times the change in concentration of B, which is the same as 1 over C delta T, which is the same. All those values, any one of them would represent the rate of the entire reaction. You can choose any one of those items and you can determine the rate of the overall reaction from it. So here we have a balanced reaction, which is methane gas with oxygen producing CO2 and water. This is the flaming bubbles from the very first day. What's the rate? The rate is the negative delta concentration of CH4 over delta T. It's negative because it's a reactant loss. That's the same as 1/2 of the O2, which is the same as 1 over 1 of the CO2, which is simply 1. And then you again have the 1/2. Notice those are positive because it is a product, therefore it's being gained. This will get interesting. That's magnesium, manganese perchlorate with hydrogen ion, which is an acid. Now this looks hairy. What's the take-home message with this? The take-home message is any one of those relationships, pick negative 1/8 delta MnO4 minus over delta T, or you could pick with water, it's 1/7 delta H2O over delta T. Those values are all the same rates. That, my friend, is a mind bender.